So the question here is derive an expression for electrical conductivity of an intrinsic semiconductor and compute the room temperature intrinsic carrier concentration for gallium arsenide full stop. Given at the room temperature electrical conductivity for gallium arsenide is 3 into 10 raised to minus 7 ohm meter raised to minus 1 full stop. The electron and hole mobilities are 0.80 meter square per volt second and 0.04 meter square per volt second. And this is the question they had asked for engineering services mains exam for the branch of electronic and telecommunication from the subject of EDC for 10 marks. So here in this question there is two parts. In the first part we need to derive the expression for electrical conductivity of an intrinsic semiconductor, and by the use of this expression and whatever formula we will derive for the electrical conductivity, by the use of that, in the second part of the question at the room temperature we need to find out intrinsic carrier concentration for gallium arsenide. So first of all we'll focus on the first part of the question, and here I'm considering in this figure as a conductor having the number of electrons as a capital N, and their length is L. For this conductor their length is L and their area of cross section is A. So here as we know that current density for the conductor, it is defined here J is equal to I by A. Current passing through per unit area is defined as current density, and this we can consider here as a unit of ampere per meter square. Now this can be called here as equation number 1, and in this one we need to substitute here this current. So how to get the current through this conductor? So this current is defined here total number of charge as a capital Q passing through this conductor in unit time is defined here current passing through the conductor. So this Q, how it can be written here? So this Q is total charge. So if this conductor containing n number of electron, and for one electron their charge is as a small e or a small q whose value is 1.6 into 10 raised to minus 19 coulomb. So here we can write this capital Q as a capital N into Q divided by T. If this charge carrier is taking capital T time to cross this conductor having the length L, then this can be written their velocity V is equal to L by T. So from here we can get it this T is equal to L by V. So let's say this as equation number 2. In this equation number 2 we need to substitute the value of T. So this can be written here NQ divided by L by V. So this can be rewritten here as a NQV divided by L. Let's say this as equation number 3. Now we need to substitute this I in equation 1. So how this can be written? This can be written here J is equal to NQV by L into A. So for this conductor their area of cross section is A and their length is L. So the total volume for this conductor will become L into A, and this capital N is called the number of electrons in this conductor. So how it can be defined here? This total number of electrons in a unit volume as a L into A is giving here the electron concentration. This capital N is number of electrons. So number of electrons in unit volume is giving here concentration of electron. So this can be written here as a small n into Q into V. So this V is called the velocity of the charge carrier, and if this conductor is placed under the electric field, then this velocity of the charge carrier is called here, this V is called here as a Vd, that is called drift velocity, and this is given here as a mu into E. This mu is called the mobility of the charge carrier and E is called electric field present for this for this conductor. So this equation 4 can be rewritten here as a N Q mu into E. In the case of conductor, the charge carrier is electron, so this mobility can be written here as a mu N. So this can be written here as a mu N. Now this J is called here current density, which we got it here as a NQ mu N into E. So this is the current because of this electric field. So that is the reason this current is called here as a drift current density. This current density J is now called here as a drift current density, and this, let's say, as a equation number 5. So this can be written here NQ mu N is called as a sigma into E, where this sigma is called as a conductivity of this conductor. Conductivity of the conductor. So now here, by the use of this expression as a J is equal to sigma into E, we can analyze, or we can apply the same thing for semiconductor also. Only the difference is, in the case of semiconductor, there are two type of charge carrier. One is called as electron and another one is called as a hole. So as a hole or as a effective, we will get that drift current due to the electron as well as hole both. So now we can write this J, that is called current density or drift current density. Total drift current density is given here. J drift is equal to J N drift plus J P drift. So due to the electron, if their drift current density is given here as a NQ mu N into E, then due to the hole, this can be written here as a PQ mu P into E, where P is called hole concentration, mu P is called mobility of the holes, and Q is called electronic charge, and this electric field is common to both electron as well as hole. So here we can write this as a N Q mu N, or we can take it here, this Q and E is common to both, so we can write this as a Q is outside. So N mu N plus P mu P, and this electric field is common here. So this can be written here as a sigma into E. So this can be compared with the previous whatever we got it here as a J is equal to sigma E. So from this, like whatever we had derived for the conductor as a J is equal to sigma into E, we can compare to this. Then we will get it here, this current density, a total drift current density is equal to sigma into E. So this sigma is called the conductivity of the semiconductor. So this sigma of semiconductor is given here as a Q into N mu N plus P mu P. But we need to define, or we need to derive the expression for the intrinsic semiconductor. So as we know the condition for the intrinsic semiconductor, if the concentration of electron is equal to concentration of hole, and that can be equated to another variable as a Ni, then now this is the condition for a semiconductor to become as a intrinsic semiconductor, to become here as an intrinsic semiconductor. So here we can substitute this in this equation. So this equation number, we can say it here as a 6. So this equation number is 6 here. So in this equation number 6, we can substitute at the place of N and P by the Ni. So this can be written here, sigma intrinsic is equal to Q into Ni mu N plus Ni mu P. So this Ni is common to both. So this can be written Q under bracket mu N plus mu P into Ni. So this is the expression what we got for the intrinsic semiconductor. This is the expression for the conductivity of the intrinsic semiconductor. And now by the use of this formula, we need to find out the intrinsic carrier concentration for gallium arsenide. So that is the second part of this question. So now I am going to solve this second part of the question. So here we can write this as a sigma intrinsic is equal to, this sigma intrinsic is equal to Q into mu n plus mu p into ni, so that this ni can be written here as a sigma intrinsic divided by Q into mu n plus mu p. And their conductivity it has given in the question, their data has given. So this conductivity of the intrinsic semiconductor is given here as a 3 into 10 raised to minus 7 divided by this Q value is 1.6 as electronic charge into 10 raised to minus 19 coulomb, and their mu and mu p value has given. So this is 0.80 plus 0.04. So whenever you solve this, you'll get it here as a 2.232 into 10 raised to 12 per meter cube. So these many number of electron hole pairs, or we can say that this is the concentration for electron as well as for the hole, or we can write in this way, this is N naught is equal to P naught is equal to Ni. So this is intrinsic carrier concentration for a semiconductor, and these mobility is having the unit in terms of like meter square per volt second, and their conductivity also had given in terms of ohm meter raised to minus 1. So ultimately their concentration of this intrinsic carrier will become in terms of per meter cube. So their volume is represented in terms of meter cube. So that is the reason we had taken the unit here as a meter cube. If you do the mistake by substituting centimeter cube, then your answer will be wrong, because in the engineering services examination, unit is having the significance over there about how you are solving the problems and how you are taking about the units. That also very much important in that conventional exam. So we must have to take care about the unit, whatever it has given the unit, and in what form we need to represent it. So by this way we got both the part of this question. One is their derivation as a this part, like what I can say, sigma intrinsic is equal to Q into mu n plus mu p into Ni, and by the use of this formula we got it here, this intrinsic carrier concentration for the gallium arsenide as 2.232 into 10 raised to 12 per meter cube. So by this way, this is the end of the explanation for this question.